All right, everybody, let's start by going over problem of the day number 4, which you guys were supposed to work on last night. It bridges chapters 19 to chapter 20. And I gave you guys a hint in the email last night because I know a lot of you have forgotten how to make aldehydes a little bit. I know we covered it in term 1 and term 2, but we're going to go back and review it a little bit. All right, so there's quite a few ways to go about this. I'll just show you the route that I chose. What I did, I started with benzene. Oh. And then I did a Friedel-Crafts alkylation.
Did you start with the bromine first?
Yep, both of them are ortho-para-directors. But in this case, the reason why I chose the alkyl group first is that the isopropyl group's very blocking, right? It's very big, bulky. You're going to prevent any sort of electrophilic aromatic substitution at that ortho position. So I would say this is a good route to go. Whoop, shoot. Got fat fingers. And then you do your bromination. Which will be directed para. What do you guys think I should do for the next step? Our final product is an aldehyde. We could do elimination maybe, but then we're still going to be left with an extra carbon on there. You could do ozonolysis, but you'd have to have a styrene derivative. This isn't a styrene derivative. It has too many carbons.
You need to add a bromine to that carbon chain.
So that's one route. If you had an ethyl group, you could put in a bromine, do elimination, and do ozonolysis. That'd be fine. But let's think of a different reaction we saw last term. So we can convert from an alkyl group, specifically a benzylic alkyl position, if there's hydrogens on it, directly to a carboxylic acid using what reagents? Yeah, sodium dichromate, the chromic acid conditions, or potassium permanganate, right? So I'll just pick potassium permanganate. That way we avoid chromium. So that would be step 1. Step 2, we want to make sure we reprotonate our carboxylic acid. So I'll just add in that second step. All right. We don't want a carboxylic acid, though. That's not our final product. What's that? Nope, that was one of the mechanisms you don't need to know. All right, what sort of intermediate should we go to in order to eventually get to our aldehyde?
A primary alcohol.
Primary alcohol. So we could react this with lithium aluminum hydride in order to get to our primary alcohol. Get a bromine on there. And then last but not least, we can go from our primary alcohol to our aldehyde using what reagents? PCC. So the reason I had this as our problem of the day is that this next chapter is going to be all on ketones and aldehydes. And we've already seen ketones and aldehydes quite a bit, and we need to remember a lot of those reactions that we covered either last term or all the way back in first term. And we'll go over which reactions you should review for this chapter. And there's not too many of them, so it shouldn't be too bad for you guys. All right. So let's go to ketones and aldehydes now. Yep.
I was looking at the problem of the day
Mm-hmm.
that you just gave us, and I think there's a typo.
What did it say?
There's no peak position, and you said it wasn't a peak position.
Oh, sorry, change that to the 1 position. It should have been 2 and 3, but it's adding into that 1 position. Sorry. Thank you for pointing that out. Let me rephrase that. All right. So if you guys have the problem of the day, change that 1 to a 2 and the 2 to a 3. the numbering was off.
So wait, one, two,
Just drop it down by one.
Yep, change 1 to 2 and 2 to 3. I'll email you guys an updated version of the pod just so we're not confused too. Sorry about that.
So the oxygen is the one position.
Yeah, the oxygen's the 1 position, the carbon next to it's 2, the one further away is 3. All right, let's start with the introduction of aldehydes and ketones. You guys have already seen these quite a bit, so I'm just going to jump straight into nomenclature. I know some people last term didn't really like the sapling videos, so I'm going to spend a little bit more time talking about the nomenclature rules for some of these. For aldehydes, it's pretty straightforward. So let's take an example aldehyde. When you number it, you always want to start at the carbon that's on the carbonyl. So we'll number this 1, 2, 3, 4, 5, 6. Right? So what would we name the parent? It would be a hexane, right? Because it's 6 carbons long. So naming this gets pretty easy. You do hexan, which is the parent, and then you add al at the end. The al is your suffix for aldehydes. All right, let's take one example for this. Let's name this aldehyde. Again, we want to number from the carbonyl, so it'd be 1, 2, 3, 4, 5.
3 bromo pentanal.
All right, but before we do that, we've got stereochemistry. What's the stereochemistry? What do you guys think? Oh man, there's a lot of debate going on between R and S.
It's R.
It should be R.
Well, I mean, R, that's what I meant.
Because bromine's priority 1. If we go out between carbon 2 and carbon 4 is bonded to 2 carbons, so that's higher priority than carbon 2. We're going clockwise around with the lowest priority pointing back, so that would be R. Okay, so now we're ready to go. We can say 3R, 3 bromo. Not quite. What else?
Oh, 4 methyl.
3 bromo, 4 methyl, pentanal. So don't forget to number it the same, or use the same system of alphabetizing that we've seen before. So in this case, bromo goes before methyl because it's lower in the alphabet. So if we look at bromine, bromine's highest priority because it's the heaviest. And then if we're comparing carbon 4 to carbon 2, carbon 4 is bonded to 2 carbons. Carbon 2 is only bonded to 1 carbon. So that makes it highest priority. We go clockwise around. That makes it an R. Okay, so now let's jump to ketones, because ketones get a little bit trickier.
And there won't ever be a situation where we have like 2 aldehydes and we can name it.
For the most part, we're going to avoid those. Yeah. So ketones are pretty similar. Let's take a simple ketone. Want me to scroll back up?
Yeah, just slightly bigger.
Okay. So in this case, is the carbon attached to the oxygen going to be priority 1?
No,
No. Which side should be priority 1, the left or the right? Probably the right. So you'd say 1, 2, 3, 4, 5. The key is you want your carbonyl CO double bond to be at the lowest position. So if we're going to name this compound, we would name this 2-pentanone. So in this case, one is your suffix. The 2 is your CO position. And so this sort of naming convention is used, suffix. This sort of naming convention is used for ketones. Another system that you might see used quite a bit is to do pentan 2-one. Either one is acceptable. It's kind of like with alcohols, where you can say 2-butanal, or you can say butan 2-al, or butan 2-all, excuse me. So you just need to make sure that what you're putting down is consistent. And the second one that I've shown is very, very common, especially if you have more and more substituents getting added on there. Another confusing thing with ketones is there's an alternative for simple ketones. But it's not really preferred. And so in this case, you could call it, ethyl methyl, there should be a space, ketone. But obviously, the system starts to break down if you run into more and more complicated ketones. There are a handful of special cases. And you guys have already seen a variety of these special cases that don't follow IUPAC naming conventions. What's this molecule? Acetone. So we don't call it, what would that be, 2-propanone? We just call it acetone. Or we could say dimethyl ketone, but nobody calls it that. Everyone calls it acetone. What about this ketone? Exactly. Is there an echo in here? All right, and then one last one that's also allowed by IUPAC but doesn't follow the naming rules. Does anybody know the name of this one? Some people might say diphenylketone, but it's more commonly called benzophenone. So all of these are special cases for ketones. There's also a couple other ones, too, that I wanted to bring up. These are usually the most common. The other one that's a special case let's do our list of aldehydes. So the first one was for special cases for ketones. All right, there's another one that's analogous to acetone, but it's an aldehyde. Yep, it's formaldehyde.
It wasn't me.
Formaldehyde used to be used in embalming fluid. Now it's used in making plywood and particle boards. It's a very strong binding agent. The next one is acetaldehyde. And the very last one is a cyclohexane ring. And this is called cyclohexane I'm going to drop it down. Carbaldehyde. So this doesn't follow the typical naming conventions. This uses the carbaldehyde prefix anytime you have a ring in there. specifically a saturated ring. So there are some weird examples. You could also include benzaldehyde in there too as being another unique example, but we've already seen that quite a bit. All right, let's review the preparation for aldehydes and ketones.
First, I have one question.
Yep.
You have like, let's say like a benzene ring and an aldehyde or a ketone on it. What takes priority? The ring or the aldehyde?
So remember when it's like a benzaldehyde derivative?
Or just like a ring with like, other substituents on it.
Ring with other substituents. Let's go back and just do practice then.
I'm just wondering what is priority.
Shoot. All right, let's do a couple practice problems. Nope.
Yeah, it does ring.
All right, the one on the left, what would that be called? You could say meta bromo benzaldehyde. Or you could say 3-bromo-benzaldehyde. That would be perfectly fine. And that's because our aldehyde is coming directly off of the ring, so the benzene naming rules come into play. The one on the right, we have to number it going 1, 2, 3, right? So if we were to name this one, this would be 3-phenyl, right? Because this whole group is considered a phenyl group coming off of there. Propanal.
So the aldehyde you keep as well would take priority.
Yeah, the aldehyde, if it's a longer aliphatic aldehyde, so in this case we've got a 3-carbon chain, you want to start numbering at the 1 where the CO double bond is, and then treat the benzene ring as just a phenyl group. If there are substituents coming off that benzene ring, it gets really, really complicated, and I won't ever throw those problems at you. Yeah. Okay, so let's go into preparation of aldehydes, and we'll cover a lot of review here. All right, the first way we know of making aldehydes is oxidation. So if we start with an alcohol, specifically a primary alcohol, what reagent do we need in order to make an aldehyde? PCC, right? And in particular, I'll give you guys a section number. So if you're looking at this saying, I have absolutely no idea where this is coming from, this was in section 13.10. And in particular, we said that this has to be a primary alcohol in order for this to work.
I like when you put the section number.
Okay, I'll keep on trying to do that. Then ozonolysis. So if we have an alkene with 2 hydrogens on it, whoops. Oops. We can get 2 equivalents of our aldehyde, but what reagents do we need? O3 and then dimethyl sulfide, so DMS. And this was in section 9.11, if you want to review it. So that was all the way back, I believe, to first term. The important thing to remember is with ozonolysis, you're going to cleave double bonds straight down the center and get 2 aldehydes or 2 ketones out of it if you're starting with an alkene. All right, the last one that we saw was...
Dr. Now, how about some of the ones where it doesn't make, because I remember, I think it was on a quiz, where we used those analysis, right, it didn't form 2.
Okay, let's do an example problem really quick. let's take this and react this with O3 and DMS. So we're going to cleave this double bond smack down the center, right? So we're going to lop off a carbon there. And what are our two products that we get out? Benzaldehyde, and then what's the little aldehyde on the right? Formaldehyde. So if you do have an alkene where you've got two hydrogens on one end, you'll just cleave off one carbon as formaldehyde.
That's not what I'm talking about.
Which example were you talking about?
I don't know, it was a quiz from last quarter. And I don't know, I don't know.
Well, if you think of it, let me know and we can go back and review it. Okay, the last one was, yep. Oh, sorry, thank you. This was supposed to be a hydrogen. If we had a CH3 there, it should have been acetophenone. Thank you. So starting with styrene. Good catch. All right, and then the last one was hydroboration oxidation. All right, so I'm going to give you guys the reagents and product, and I want you to give me the starting material. What starting material would we need? We're using the really bulky boron, right? 9ppb is huge, so it's not going to be an alkene. An alkyne, right? Exactly. So in this case, you need a terminal alkyne. And it will do anti-Markovnikov chemistry. So we'll add in a carbonyl at the terminal carbon. And if you remember, it will do that quick tautomerization because it's under base catalyzed conditions. And so you'll form an enol that will quickly tautomerize to your aldehyde. And this was in section 10.7. All right, so most of those are review. If you are really rusty on them, I would recommend going through your lecture notes and trying to review them. Now let's go to reviewing ketones. All right, with ketones, again, we have oxidation. So we could use PCC, or we can use Na2Cr2O7, sulfuric acid, and water. And if we do this, we can get to a ketone. What sort of starting material would we need? A secondary alcohol, right? So if you remember back to the chapter where we had alcohols, if you've got a secondary alcohol, you can only oxidize it to the ketone. And this was from chapter 13.10 again, if you want to review. The next one, just like with aldehydes, was ozonolysis. And so with ozonolysis, you can start with an alkene, react this with ozone followed by dimethyl sulfide, and you can get two equivalents of a ketone. And this was from chapter 9, section 11. All right. The other one that's very similar to what we've already seen was our acid catalyzed hydration. which is also a review back from chapter 10 when we covered alkynes. But in this case, we're going to do anti-Markovnikov chemistry. And we can end up forming an enol that tautomerizes to the ketone. What reagents do we need? Yeah, sulfuric acid, and then what's the catalyst? Yeah, mercury sulfate, so.
Is that blue dot really on the anti?
Or sorry, the blue dot's Markovnikov. Did I say anti-Markovnikov? Yeah, sorry, I meant to say Markovnikov addition. And this was section 10.7. So make sure you're familiar with the tautomerization mechanism. All right, what's the other way we know of making a ketone? It's relatively new.
Acylation.
Yeah, acylation, and it had Friedel-Crafts acylation before it, so we'll include that because that's a new one. So we do have a new method of making ketones. Specifically, if we have benzene, we need an acid halide and aluminum trichloride. And if we do that, we can install a new ketone directly onto a benzene ring. What's the limitation with the Friedel-Crafts acylation? When will it not work? Yeah, when your benzene ring is strongly deactivated, the Friedel-Crafts acylation will not work. So that's an important key to remember for these reactions. All right. I know a lot of this is going to be review, but we're going to build upon it really quickly. So I want to make sure we're all fresh with the new material or review material. All right, nucleophilic addition to ketones and aldehydes. We've seen this already when Grignard reagents are used to add into a ketone or aldehyde, but we're going to talk about this in a lot more detail. So first thing I want to do is I want to talk about aldehydes and compare them to ketones. If you think about an aldehyde, just our generic aldehyde, we can draw a resonance structure of this, right? Where the oxygen has a negative charge and the carbon has a positive charge. So if you think about it, which position on an aldehyde is going to be very electrophilic? Which site wants electrons? The carbon, right? It's got a partial positive on it, so we could say this is a good electrophile. And we can also think about it just simply due to induction. So we can invoke resonance to explain its electrophilicity, or we can propose induction. The reality is it's a little bit of both. And if we're explaining it in terms of induction, we're just saying that oxygen's more electronegative, which means that that carbon is going to be a good electrophilic site. Okay, so now let's compare this to ketones. And again, we'll do the same thing, and we'll compare resonance and induction. So if we have a ketone, the resonance structures look almost identical. We were just replacing that hydrogen with an alkyl group. Or we can explain it in terms of induction, where the oxygen's just simply more electronegative. But in either case, the carbons on them are good or electrophilic sites. Okay, so now I've got an abstract question for you guys. They're both electrophiles. Which one's the stronger electrophile? So I heard a bunch of people say the aldehyde. Why do you guys think the aldehyde's the better electrophile? So the only difference in these is this R group and the hydrogen. And an alkyl group, is that electron donating or withdrawing? Donating, right? Via hyperconjugation. So if this is donating electron density into the carbocation, is this making the carbocation more or less stable? More stable, right? So we can conversely say because this one's less stable, it's going to be more reactive. So you can think of the reactivities just in terms of the resonance structure. And we can say that this top one is less stable more electrophilic. And then this one we can say is less electrophilic. Because these R groups can donate electron density. And stabilize the carbocation. What do we call it when an alkyl group donates electrons? We refer to induction, resonance, hyperconjugation. So it's a little bit different. It's not physically pushing electrons in. It's more just that the sp3 orbitals nearby can help stabilize that positive charge on that sp2 lobe. All right. The other thing that's interesting to think about is which one is more prone to a nucleophilic attack, an aldehyde or a ketone, and why? Aldehyde. So if you're thinking about trying to squeeze into a tight place, right, you don't want stuff blocking you. The aldehyde only has a hydrogen. The ketone has methyl groups. So if we're thinking about it in terms of sterics, we can say that the aldehyde is more electrophilic just simply because it's more accessible. So we can say also sterically more accessible. So if we're looking at these, they're both good electrophiles, but aldehydes are a lot more electrophilic than ketones. And we'll see how this plays out with some of their chemistry too. So now let's go and do our simple mechanism, which most of you are very familiar with already. In fact, we already had it on a problem of the day. And I'm going to call this basic rather than acidic, because there is an alternative where it's acidic. And I'm just going to choose a ketone. It can be a ketone or an aldehyde. And if you've got a nucleophile, the nucleophile is going to want to attack that electrophile, kick up electrons onto that oxygen. You end up with an oxygen that has a negative charge. And then last but not least, you have a proton transfer. So I'll just call this H+, where you can protonate your alcohol and you can form your alcohol. So the key is, this is broken down into 2 steps. The first step is nucleophilic attack. The second step is our proton transfer. Does this look familiar to people? What sort of nucleophile have we seen where it does this? Grignard reagent. Question is, why am I showing this as an equilibrium? Were Grignard reagents in equilibrium? No. The interesting thing is you can actually draw this reaction going backwards, and you could say, well, what if this oxygen kicks down and then kicks off your nucleophile? Is an alkyl group, meaning the conjugate base of an alkyl group, a good leaving group? Do we see methyl groups pop off and act as leaving groups? No. So in a Grignard reaction, this is a one-way street, but with a lot of nucleophiles, there is a very significant amount of equilibrium occurring because the nucleophile itself can act as a reasonable leaving group. In a Grignard reaction, the Grignard is a terrible leaving group, so we only show it as one-way arrows. Oop. All right, so now let's take a look at the simple mechanism, but under acidic conditions. All right, so the first step in a acidic mechanism is you still have your ketone, but the fastest reaction in chemistry is what? Acid-base, so that's going to be the first step instead of the last step. And where's the basic site? Not the carbon. The carbon has a partial positive. The oxygen, right? The oxygen has a partial negative. That makes it a reasonably good base. So in this case, we can throw in a strong acid like sulfuric acid or tosylic acid, which is an organic acid. And we can protonate our ketone. That gives the oxygen a positive charge. We can draw a major resonance structure for this, where we can say, well, now the carbon has a positive charge and the oxygen's neutral. That means this carbon is now super electrophilic. And so the next step will be our nucleophilic attack. And our nucleophile in these reactions is typically not something that's negative, because something that's negative is also a strong base, right? It would just deprotonate. So in this case, we still have a nucleophile. Usually it has a lone pair. And we can say, all right, this nucleophile can just add into that site, right? And when we do that, we still have our alcohol up there. But now our nucleophile has a positive charge. And then what you need to have at the last step is some sort of proton transfer. Deprotonate it. And I'll just draw this as negative H+. Actually, let me do it this way. Just keep it consistent. Sorry. Our nucleophile is added in. We get the same product as under the basic conditions. But we've regenerated our acid.
Are you using a base in acidic conditions?
Really, it needs to be a very, very weak base, because if you've got a protonated site there, you can do that. The other thing to look at, too, is its equilibrium, right? Acid-base reactions are always under equilibrium. Oftentimes with these, it depends on pKa, so we'll go through specific examples for these. And not all of these are the same step, but oftentimes you have that final deprotonation step because the nucleophile that adds in is neutral. That's a good question, though. All right, so these are two relatively similar reactions. The key is for the basic mechanism. The first step is the nucleophilic attack followed by proton transfers. In the simple mechanism, the first step is your proton transfer. Followed by your nucleophilic attack. So the order is slightly flipped for these, or not slightly, it is flipped for these two reactions. Okay, the important thing to remember for these reactions is that the reactions are in equilibrium. So let's make a list of important notes. The first one is the reactions are in equilibrium. That's an important thing to remember. So it's not that they're one-way arrows. It's oftentimes they're quite reversible. The next one is if the nucleophile is a good leaving group, and the equilibrium often favors the starting material side. And we said with the Grignard reaction that the Grignard reagent is in a good leaving group, so we showed as a one-way arrow. That means it favors the product side. But hypothetically, if our nucleophile were something like a halogen, that could pop off very easily and we'd go straight back to our starting materials. Conversely, if the nucleophile is a bad leaving group, then the reaction favors the products. All right. Also, the last thing I wanted to mention for the important notes is if we're comparing aldehydes and ketones, which one's going to favor formation of your nucleophilic addition product more? Aldehydes, and why is that? Because they're more electrophilic, right? So if it's an attack between a nucleophile and electrophile, if you have a less stable electrophile, it's going to favor that attack a lot more than if you have a moderately strong electrophile. Since they are more electrophilic. It's not absolutely cut and dry, though, because you oftentimes have to compare the stability of your nucleophile and electrophile. It's just in this case, if we're only comparing electrophiles, aldehydes are the stronger electrophile. All right, so now let's think about what nucleophiles we can use for these reactions. All right, let's start with oxygen. What would be a common nucleophilic source of oxygen? Yeah, or we could just say even water, right? So if we're dealing with just neutral sources of carbon, we could have water. We could have alcohols. Oops, sorry, that should be a OH. The other one that we're going to see in coming portions of this chapter are diols are actually very commonly used as a protecting group strategy for ketones, and we'll see that later. The next one are sulfur nucleophiles. You can have H2S, which is a gas. It's somewhat poisonous, but it works. Or you can work with dithiols, and again, these are commonly used as protecting groups. Let's think about nitrogen. Oops. We could have an amine. It's a primary amine, so these work well. We could have a secondary amine. You guys think a tertiary amine will work?
Sure.
What do you notice about all of our nucleophiles so far? They all have hydrogens on them, right? So in this case, a secondary amine isn't that stable because if it were to add in, it would be a good leaving group. So it's important to remember that you can only use primary or secondary amines. All right, the next one will be hydrogen. And we've seen these two. For reducing conditions. So sodium borohydride and lithium aluminum hydride are commonly used as hydrogen nucleophiles. Then the last one I wanted to quickly squeeze in is carbon nucleophiles. We've already seen Grignards. We can have cyano groups. Oh. The key is you probably don't want to have HCN. And why is that the case? It'll kill you. That's the most important reason not to use it. You don't want to use cyanide in the lab unless you're really, really gutsy. And then the last and strangest looking one I wanted to show you guys is this phosphorus reagent, which is used in the Wittig reaction, and we're going to cover that later in this chapter as well. But essentially, we've got an option for installing a bunch of different nucleophiles into ketones and aldehydes, and we're going to sequentially go through these over the course of this chapter. All right, I think that's where we're going to leave it today. I'll email you guys the corrected version of the problem of the day, but just remember that the 1 on the furan ring should be the 2, and the 2 should be the 3.